All right, so let's talk about points, lines, segments, rays, and planes. We're going to be able to identify all five of those. We're going to name all five of them. We're going to determine lengths of segments on a number line, and we're going to utilize the additive property of length. Okay, so a point. What is a point? A point is very difficult to identify. We can talk to this guy named Euclid. Euclid is said to be the father of geometry. He wrote 13 books on it, and that is the foundation of geometry that we use today. They are called Euclid's Elements, and the first chapter of the first book is defining a bunch of stuff. And he defines a point as that which has no part. I'm sure any of you could draw a point for me or identify a point, but that's a point. It is location only. It has no part. It has no depth, breadth, width, length, anything. It's just a point. Generally, points are labeled with capital letters. So that could be point A, and this could be point B. You could have a point C down here. Those are points. That's how you start geometry. Then there's lines. Euclid defined a line as a breadthless length. A breadthless length. It is something that has length but no width. It is like a piece of string, except a string has width. A line is nothing. When we draw a line, we could measure the thickness of the line, but in reality, we can measure the thickness of our pencil or the pen or the marker or whatever we use to draw the line, but we can't actually measure the width of a line. It has no width. And Euclid says the extremities of a line are points. What he means by that is that you can kind of think of them as endpoints, but lines don't have endpoints. It's just kind of the ends that we would draw, because we can't draw a line going on forever, because we don't have enough paper to draw forever. And then also a straight line is a line which lies evenly with the points on itself. So, according to Euclid, that's a line, and that's a straight line. Whenever we refer to a line, we are going to be talking about a straight line, but we're not going to define it. We're not going to say, hey, that is a straight line. It's just going to be a line. Whenever we're talking about things like this would be considered a curve, and this is a line. Now, whenever we would like to name a line or be specific about which line we're talking about, we need to identify at least 2 points on the line, which is why Euclid says the extremities of a line are points. Well, if I have points A and B on this line, I would call this line AB. That's how I would say it verbally. If I wanted to write it down, I would have A and B right next to each other with a line on top of them. This means line AB. Line AB is the exact same as line BA. It doesn't matter what order you put the points in, those both mean the same line. I could even, if there was a third point on this line, maybe D, line BD is also this line. As long as you name 2 points that are on that line and put that line over it, you're talking about that line that goes through points B and D, points A and B, points B and A, points A and D. All of these all reference this one line here. They're all correct references of that line. Neither one of them is more correct than the other. That's different ways to name this line. Another way, if possible or if notated, lines are sometimes also named with lowercase cursive letters. So I could call this line L, or I could call this line M. Now, the tricky part with that is, unless that's written down on the diagram, if you just say, yeah, line L, I don't know what you're talking about. You can always name a line using these. This, you can only use the lowercase cursive letters if it's drawn like that on the diagram. Lines. After lines comes rays. A ray is a line with one endpoint. Now again, I'm saying line. I'm not saying straight line, but we've specified that a straight line is a line. A straight line is synonymous with a line. And anything else, any curvy lines or swishy lines, those are going to be called curves. So if we're talking about a line, a ray is a line with one endpoint. So a ray goes from here off for forever. It has one endpoint and it goes off forever. Now to name a ray, you need the endpoint. Let's call this point S, and another point on it, Q. Now, naming rays is a little bit more specific than naming lines, because when you name a ray, the first point that you identify has to be the endpoint. So this being ray SQ is correct. I cannot call this ray QS because Q is not the endpoint. You have to start with the endpoint. And similar with lines, you have to put a little picture above it, and with a ray, we're going to draw a ray above it. So this is ray SQ. And just looking at this, if I didn't see the diagram, pretend I didn't see the diagram, and you tell me that there's ray SQ, just by hearing that, I know that the endpoint is S. The endpoint of this ray has to be S because it's the first point you say when you named that ray. I cannot call this ray QS. I cannot do that. Now I can have multiple rays in a line. So let's say I have a line right here, and this is M and O. Now if I talk about ray MO, that exists. Ray MO exists. It starts at M and goes in the direction of O. That's fine. You can have that. Furthermore, I could also have ray OM, because ray OM starts at O and goes through M. So I can identify different rays within the same line. That's possible. Also, there are opposite rays. So let's say I have this third line, and this line has, we're going to put 3 points on it. PQR. Nope, don't want to use Q again. PRT. Now I can create 2 rays from this line. I can say that ray RP and ray RT. Ray RP and ray RT are what we call opposite rays. Opposite rays, they share an endpoint and they go in opposite directions. That is key. If they do not share an endpoint, they are not opposite rays. They have to share an endpoint. So these two are opposite rays because they share an endpoint. They both start with R, and one goes in the direction of P, and one goes in the direction of T, and those are in opposite directions. So they are opposite rays. So 2 opposite rays would be linear. They would have to make a line. If they don't make a line, they are not opposite rays. Cool, that's rays. Thirdly, are segments. Euclid calls a segment a line with 2 endpoints. No, he doesn't. Euclid never defined a segment, but we do. So a segment is a line with 2 endpoints, meaning it stops on both ends. So if I have an endpoint here going over to another endpoint here, z and y, if I have a segment between points z and y, that is a segment. It does not go forever. That's the difference between a line and a segment, and why a ray is even different from that. Now, I can call a segment, I can call this segment by two names. Either zy or yz. And the symbol that goes above a segment is just a line. Well, it's not a line because it doesn't have arrows at the end. It's a segment. So zy or yz. Now maybe I have some point x in here. Segment zx is just this little bit in here. So segment zx is here, segment zy is here. When you name a segment, you have to use the endpoints of that segment. We could say there was another one. Well, also, xz, that is the same as that one. We could draw or name another segment, xy, and yx. That's another segment. So there are three segments just with these 3 points. There are 3 different segments. And that's segments. So let's continue. Planes. So planes are Euclid. This one is defined by Euclid. A plane is a surface that has length and breadth. Surface which has length and breadth. I don't think that is supposed to be in there. A surface which has length and breadth only. Meaning, it goes this way and it goes this way, but it does not go this way. That's space. We're not going to talk about space. We've talked about a point, which is this. A line does that. A plane goes in this direction then also. So the extremities of a surface are lines, and a plane surface is a surface which lies evenly with the straight lines on itself. All right, well, let's see if I can draw a surface. Maybe it goes up like that, and then this front piece goes down like that, and then this back piece is also like that. This back piece does that. So, according to Euclid, that is a surface. It's all wibbly and wobbly and wavy. Like a flag. Like a flag that's blowing in the wind is a surface. If you were to lay a flag out flat, like that, where it's just flat, that is a plane surface. Now, we don't call them plane surfaces anymore. We simply call them planes. It is a flat surface. And we actually work not any time. 95% of the time, we work with a two-dimensional surface. 95% of the time, we're going to be working in a plane. Most of our drawings will be drawn in a plane. If they are not in a plane, that will definitely be told to you. And yeah, so that's a plane. So Euclid says the extremities of a surface are lines, meaning that if you want to draw a plane, you have to draw lines around it. If you wanted to draw a line, you have to draw points around it. So that's the extremities of a line are points. In this case, the extremity of a plane, the extremities of a surface or a plane are lines. Yeah, I was going to say something I forgot. So when you name a plane, so let's all agree that that's a plane surface. It is a plane. To name a plane, you just have to pick 3 points on that plane, specifically 3 non-collinear. Try and figure out what non-collinear means. There's 3 parts to it. Non, co, and linear. What do you think non-collinear means? If I pick 3 non-collinear points, A, B, and C, I can just call that plane ABC. There you go. That's it. And similarly between lines and planes, sometimes planes are defined or are named by like bold capital letters. So I could call this plane X. So I'm going to draw a big bold X. So plane ABC and plane X, those are the same thing, because in the diagram I say, hey, this plane is called plane X, and it has points A, B, and C on it. So plane ABC and plane X are the same thing. Also, this plane does not stop at the lines. I draw the lines so that you can see the plane, but this plane technically goes off forever. Same as lines, we kind of have to draw arrows at the ends of lines to say that, hey, this plane goes off for forever. I'm sorry, this line goes for forever. I want to do the same thing with this plane, but I don't really know how to draw arrows on the ends of a plane. If you can, that's great. Do that, and then show me. But the way this is, these are not the boundaries of the plane. A plane goes forever. Same as a line goes forever. It's just a line goes forever in one direction. A plane goes forever in 2 directions. So it's going forever this way and this way. And it's forever big. So planes don't necessarily have to have edges. They can. They don't have to. But this plane X, just goes forever in all directions. 2 directions. This way and that way. Now the ruler postulate is a whole lot of words that says something very simple. Very simple. The points on a line can be paired with the real numbers in such a way that any 2 points can have coordinates 1 and 0. Wow, that's a whole lot of words. All that's saying is that if I have some line and I pick 2 points on it, I can say that's 0 and that's 1. It also says if I draw another line and I pick 2 points on it, that can be 0 and that can be 1. That's all it's saying, is that I can pick 2 points and label one of them 0 and one of them 1, and I can do that however I want. It doesn't say that 0 and 1 have to be this far apart. Unless you're like actually using a ruler, then they have to be an inch or a centimeter apart. But if I'm just drawing a line, I can put the 1 and the 0 wherever I want. I can have them this far apart, I can have, well, I guess you can't see all that, this far apart, or I can have them this far apart. It doesn't matter. Part 2 of the ruler postulate says, once a coordinate system has been chosen in this way, the distance between any 2 points equals the absolute value of the difference of their coordinates. All right, that's a whole lot of stuff. So I'm going to write that using variables and math stuff. The distance between any 2 points equals the absolute value of the difference between the 2 coordinates. So the distance is the absolute value of A minus B. Why is it the absolute value? We'll talk about that. So what this is saying is if I have some point, or if I have 2 points here, and so let's say 1 and 0 are way down there somewhere, it doesn't really matter, and I have this other point A and this other point B, and maybe A is at 17 and B is at 32. The distance between A and B is the absolute value of the difference of their coordinates. So if I take 32 minus 17, the absolute value of 15 is 15. So this distance is 15. So if I take the absolute value of the difference of their coordinates, I get the distance between the 2 points. So the question is, why do I have to take the absolute value? Well, what I could do, maybe this is negative 32 and negative 17. Well, negative 32 minus negative 17 is negative 15. But the distance between 2 points is never going to be negative. It's never going to be negative. So distance is always positive. So the distance always has to be the absolute value of the difference of the coordinates. Yes, that is good. And the segment addition postulate says if B is between A and C, then AB plus BC equals AC. Something I did not say, I forgot to mention. So let's say this is points, these should be capitalized. Let's say that's point A and B. And this should be capital A minus capital B. This was 32, this was 17. This distance, the distance between A and B, can be notated by just saying AB. AB by themselves, without anything over the two letters, means the distance between points A and B. That's it. A line with 2 points has a line above it. A ray has a ray above it. A segment has a segment above it. Distance has nothing above it. So if I just write AB, you should read that as the distance between A and B. So if I just write AB, that's the distance between A and B. So when we look at this, the distance between A and B plus the distance between B and C equals the distance between A and C. That kind of makes a lot of sense. If I have some line here, and B is between A and C, so maybe B is right here, A is right there, and C is right there, the distance between A and B plus the distance between B and C is the whole distance between A and C. So that's all that says. It sounds pretty complex, but that's it. That's all it's saying. The distance between A and B plus the distance between B and C equals the total distance between A and C. That's it. It's not that complex. The thing with math is that when you're describing something, you have to be very specific. And sometimes when you are very specific about something, it can sound a little more complex. But that's it. I think that's it. We'll see if there's another slide. But the segment addition postulate, if I add two segments together, that gives me the total length of the segment. That's really all it's saying. And that is the end.